Hi everyone, thanks for having me. So the informal split that I guess will happen over this morning is that I give you the basics of the BKW algorithm, and then Thomas will take over and tell you what is the current state of the art in applying BKW to solving the learning with errors problems. If these acronyms don't mean anything to you yet, that's good, because I spent some time on actually explaining those. So what will I do? I will give you a brief introduction to kind of what is the problem that we're trying to solve. And then to warm up, what we're going to do is we're going to revisit Gaussian elimination, right? Because it's always fun to look at Gaussian elimination. And then we think about solving decision LWE with BKW, moving on to what happens if the secret is exceptionally small. And then I hope to provide a bit of transition for Thomas to say, like, okay, so what's the problem with this approach? And then he can write in and save the day. Okay, so it's plausible that you will see a slide like this many times today, but I get to go first, so I get to do it anyway. So the learning with errors problem is a problem that was first defined or formalized like this by Oleg Regev in 2005, and it's really deciding the consistency of a linear system with some noise. So you have a public matrix A, you have some secret S, you take the product and then you add some small noise E to it, and then you get some C. And your job is to decide, well, so given A and C, was my C formed like this? So is this E small, or is it some uniformly random crap? Okay, so that's the decision LWE problem. Decide, is C formed like this, or is it something uniform? And then I said small. But the whole problem is to find mod Q. And we all know mod Q, the notion of small, makes absolutely no sense. So what do we mean when we say small? We typically mean we represent our elements mod Q between minus Q half and Q half. And then by small we mean distance to 0 in that representation. And then by the distribution we mean a discrete Gaussian distribution. For the purpose of this talk, really you can think of a Gaussian distribution, but you only take the integral points. It's not quite as simple, but really it doesn't matter for the purpose of this talk. And by now you already should have picked up, there are quite a few parameters of this problem, right? So there's a dimension n, and then there's a modulus q, there's the size of the noise, which we usually denote by alpha q, so alpha is some fraction of q that determines how big the noise is, and then you have a certain number of samples. And typically, like what you might want to think about is q, something like n squared maybe, alpha q is square root n, so n is the main security parameter, and then m is, for the definition of the problem itself, is pretty much as many as you want. And then in cryptographic schemes, you don't really get as many as you want, but the problem itself is really defined. You have an oracle that gives you samples, so you can press this button as often as you want. Okay, and one of the nice things about this problem, right? I've just given you a problem. Who knows what this could be nice about? But before we get to any potential applications and so on, what makes it interesting for cryptography is that actually we have a nice reduction. And that means we have some, by the standards of cryptography, good assurances that this is a hard problem. And it has been shown that if you can solve LWE, you can solve the shortest vector problem, which is a well-studied problem in mathematics, so, we have some confidence. And so all is nice and well, right? But the problem, so let me rephrase that. So it's nice to have some asymptotic guarantees of complexity, right? Saying like as n goes to infinity, this behaves like this. But then we want to build a crypto system. We want to say, okay, I now want my 128-bit security, and I want to pick n. How do I pick my n? Right? That's something that we have to do when we want to move this from a nice object that we study because it's elegant and so on, to something that we actually use to build cryptography. So it's really the question, so given m, n, q, and my noise distribution, how many operations, say mod q, do I need to solve this? Right, that would be a question that we have to ask as cryptographers. There's a variety of solving strategies. Pretty much the two dominant ones would be this. You can recognize that this problem actually is a bounded distance decoding problem, which is something that people have looked into. So what you do is you try to find an S prime such that the distance of a y, which is a times s, to c, which is our target vector, is minimized. Right, so it would be one strategy of going about solving this. If you find an S prime, then you know actually my C was formed like this. Other approaches, you solve the short integer solutions problem. So what you do is you try to find a short y such that y times a gives you 0, because then when you take the inner product of y and c, you get something small, because the y times a cancels out, and so you have the y inner product e. Y is small, E by definition is small, inner product is still small. Right, so that would be a strategy. And in this talk, this is actually what we're going to do. We're going to solve SIS, we're going to use combinatorial techniques, and we're going to pretend we have as many samples as we want. Okay, so how are we going to do this? As a warm-up, let's reconsider Gaussian elimination. And because it's nicer to draw matrices instead of these really narrow vectors, so now I'm effectively defining many of these LWE problems in parallel, so I have C11 to C1L, right? But you can think of this as one column if that makes it easier for you. So, and then say there are no errors, right? How would I decide the same problem? Well, I take my matrix, I concatenate A and C, and then maybe I run Gaussian elimination, and then only if the lower part here is 0, then my system was consistent to begin with, right? So it's a pretty standard linear algebra kind of technique to decide if your linear system is consistent or not. And then in the form of a picture, this is how it looks like. You do your Gaussian elimination on your matrix A, and then you apply the transformation matrix on your matrix C, and then you ask the question if you get 0 on the right-hand side. You can tell I really like linear algebra, right? Because like linear algebra people really like to draw these kind of pictures. There will be more of them. So sorry, that's the way I think about these problems. Okay, but that's linear algebra, right? That has been solved. It's easy. So let's move on to something noisy. Solving decision LWE. And the algorithm, as you gathered from the title, is the BKW algorithm. And that's actually an algorithm that was first proposed for the learning parity with the problem, the LPN problem. So you can think, if that doesn't ring a bell, then you can think of that for now. We can redefine it as a special case of LWE, even though it's much older than LWE. And so Blum, Kalai, and Wassermann, they came up with this algorithm that actually solved the LPN problem in slightly sub-exponential time, which was a big news when this algorithm came out. And so the first step, what we're going to do is we're going to retool this algorithm to apply to LWE. Okay, so how does it work? Well, I told you there will be pictures, so hey, here's another picture. So what's our goal in the noise-free case? We check if this is 0. And then clearly, that makes no sense in the noisy case, right? So the thing can't be just identical to 0 because there's some noise. So over F2, small really doesn't make any sense, right? So I have 0 and 1, what do I mean by small? So what we mean by small there is like, well, many of them are 0, right? That's what we mean by small in the LPN case. So if you have a strategy like this that is kind of based on this Gaussian elimination, then you better have something sparse there. Because if that's not sparse, it's just a random matrix, right? So that's your goal over F2. And then mod Q, what you want is the question that you asked. So you want to produce a matrix like this, and then you say like, okay, is the result small? Where small is this funky definition of small that I mentioned earlier. And so, okay, let's do that with Gaussian elimination, right? This is where we want to go. Let's use the same strategy that we used before. Let's run Gaussian elimination. We have our matrix, and we want to check whether it was formed like this, or whether C is just some uniform random stuff. If you recall Gaussian elimination, what you do is, well, you work on the columns, and then you say like, okay, let me use A11 to clear A21. So I scale the first row appropriately to subtract it from the second row. Right? Straightforward Gaussian elimination. What I've just done is when I look at the last column, I've just scaled my error E1 from the first row by effectively a random element. So if my E1 and E2 were small to begin with, they're definitely not small anymore. Right? So in just one step, I have undone all the great things that were given to me. So that's a really bad strategy. But even if A21 over A11 is not random, even if I get lucky and this is 1, I just doubled the size of my noise because I'm adding E1 to E2. So even then, kind of, this is really annoying because I'm really making this big fast. And I don't want this to be big. I want this to be small because at the end I want to check if this is small. So my problem is additions and multiplications increase my noise. And the way I'm going to deal with that is to say like, well, I have many, many rows. So I can choose carefully what rows I add in order to minimize multiplications and additions. Let's see how this is done. What we do is we cut our matrix in blocks of columns. So in this example, my block size B is 2. And then like the number of blocks I have is something in the order of log n. And then what I do is I write down a table, right? I go through my matrix and then I look at the first 2 columns and I say like, hey, 0, 0, I haven't seen that, let me put that in my table. Hey, 0, 1, I haven't seen that, let me put that in my table. I do that until my table is full, right? After at most q to the b, like eventually after q to the b elements, my table is full because it holds q to the b elements. Right, so I produce a table for every possible combination of elements in my first block. And then what I do is I use this table to eliminate. Right, so I've taken some rows out of my matrix to say, okay, these are now in my table, and then I use my table to eliminate the rest. So what I do is I've produced my table, I have my matrix, and then in my example, A21, A22 is minus 2 q over 2 and minus q over 2 plus 1. So I subtract them and I get 0. So what I've just done, at the cost of maintaining these tables, I now only did 1 addition to kill 2 columns at the same time. Right, so the noise increases because I just did an addition, but it doesn't increase that much. So that's nice. And then when you put all this together, what you end up with is an algorithm that has roughly q to the b of complexity. Right, so these tables, they're really, kind of the size of these tables really determines how long this algorithm runs. And then we worked out the details for you in this paper called On the Complexity of BKW on LWE. Okay, so that's straightforward BKW for solving LWE. Good. So a common setting in cryptography when we use the LWE problem is actually that the secret vector S is not something that is chosen uniformly at random. But instead, what we do is we pick a very small vector. Say, we still define it mod Q, but actually all the components of S, they are 0, 1, or minus 1, 0, and 1. And this is because A, it's a lot faster to add things than to multiply them, and B, actually some of the advanced features that we really like, you can only realize if you have this additional flexibility of the small secret. So in particular, something that was proposed to realize efficient fully homomorphic encryption is a technique called modular switching. And for that, you really need a small secret. And this modular switching thing is a really neat trick that makes you enables you to do homomorphic encryption a lot more efficient than you would do without it. And in a nutshell, so this is the summary of the rest of the talk. So those of you who have ever written C code kind of can now check your email. So modular switching essentially is nothing more than casting to a float. Right? So you have a double precision number, you cast to a float, you have just modular switched. Lazy modular switching, which is the thing that we are proposing, is instead of actually casting to a float, I'm going to say like, well, I'm going to check if the absolute value of my thing is below a certain threshold. And I didn't know if you had any C experience, but there's this thing, never actually compare a floating point number to 0, you always compare to some threshold. But really what our lazy modular switching does is you play around with what do I consider to be 0. And anything was below a certain threshold. Right, and then that's it, right? So, thanks.
No.
That's the... So, let's make it slightly more rigorous. Let's start off with a sample AC, right? A is my vector, C is my component of the C that I'm trying to test. And then let's assume that C is actually formed as an LWE sample. And then let's have some P, which is smaller than Q. And then modular switching really is, you multiply by P over Q, and then you scale the thing to the nearest integer. And then for a vector, you do that component-wise. And why does this work out? Well, let's unpack what P over Q times C is. Well, P over 2 times C, well, we know the definition of C, so let's put that in here. Right, so it's the inner product of A and S, also multiplied by P over Q, and then we also scale the error. And then in the next step, what we have to do is, this is the guy that we're actually having on the left-hand side, and then there's some left over here, right? So I just expanded this guy into these two guys, where I took the left-hand side out of the expression above. And then in the next step, what I'm saying, like, well, then rounding to the nearest integer, so that adds at most a half, right? So let's just kind of make that explicit. And then in the last step, I'm just deciding to call this thing the noise now, right? And that's the thing that when I'm actually scaling the between minus a half and a half times S, that gets rounded off. And so because in this inner product here, I'm actually including this S. If my S is not small, then this thing will not be small, right? So if S is a uniform random value mod Q, then this thing will certainly not be small. But if this is very small, then the rounding noise, which is the inner product of whatever is left over, rounded away from A, inner product S, that's what's left over, so this has a chance of being small. And then you can use that to pick out kind of what is a good, the smallest P I pretty much get away with. So what you're trying to do is you're trying to balance the contribution of the rounding noise with the noise that was already there, and then you end up with a P that is roughly kind of this size. And as you can see, it depends on the size of the standard deviation of the secret. So you better want that to be small. And then what you end up with is if you just do that, right? So you take your instance and you have a small secret. You do your modular switching, so you compute with the floats instead of doubles, then your complexity drops to pretty much P to the B instead of Q to the B. And since P to the B, P is smaller than Q, you end up with a smaller complexity. And you can pretty much make it happen so that pretty much B doesn't really change. Right, so that's straightforward modular switching. There was no lazy in there.
Asymptotically?
Pardon?
Asymptotically in all LWE parameters, does it give you some symmetry?
If you
can't see it, so P is Q times square root of M? Or?
No, it wouldn't kind of, it would just improve the bit security, the constants, yes. You will play around with the constants.
So this is about decisional, right? So it's not extracting.
Yeah. But the way you usually do the extraction is by you run the decisional and then you run it often enough and then extract. Yeah.
Okay, so this is basically the complexity of the overall algorithm also. Right?
Yeah.
If you want to do extraction.
Pretty much.
Okay.
So, for consistency with literature, let's put a big O tilde around it.
Yeah.
No, you can. It's pretty much the complexity. So yeah, true. Yeah, so it's not an asymptotic improvement, but you do reduce the constants a bit. And then for practical parameters, so when you say like I want to bang on have 128-bit security, reducing that to say 110-bit security is considered to be bad news, right? So that's why we care.
Is it actually clear that it's not an asymptotic improvement? So
is
it easy to see? just from the formula?
From that formula, no, but I did convince myself at some point. Let me try to. Yeah, let's maybe take this offline. Maybe somebody sees it immediately.
If you apply it to cases where Q would be very large, it can happen that Q is exponential for certain crypto systems like fully homomorphic encryption. Then you get something pretty much yes.
Okay.
Yeah, it's true. Yes, if you have a very you can make your Qs in such a way that really gives you an yeah, true. Right, but that was straightforward modular switching, right? All we have done so far is we took a technique that is used to improve the efficiency and just use it as a pre-processing and then ran our standard attack, right? We haven't actually adapted any algorithms yet. What we then did in this paper at PKC last year is to say okay, instead of just rounding everything down to floats, what we're going to do is we're going to stay in the doubles, but we're going to compare in the floats. And that is lazy modular switching for you. What we're going to do is say Q is 16 and P is 8. And then we have this vector -3, 2, 4. And then remind yourself that we're looking for collisions, right? We're trying to find a vector that matches our target vector in some table, right? And so in the standard BKW, what we would need is we would need something that is plus minus 3, right? So we add or subtract that. And now if we do lazy modular switching, you say oh, it's actually cool if it's plus minus 2 as well. Right? We don't care about the lower order bit, the least significant bit. Right? So that is fine as well, and we're happy to take that. So we're just going to ignore the lower order bits. So as a consequence of that, so now when I pick 2 instead of something that starts with 2 instead of something that starts with 3, I might actually produce something that has not 0 in the first component, but actually 1. But by the funky definition of small that I've given earlier, well, that's small. And I might be able to get away with that. And so this slide really tells you that I come from a world where we flip bits. So I'm thinking about this as lower order bits and higher order bits, which is very different from, I guess, how many people think about this, but maybe it's helpful to some of you. And so what we're going to do in this kind of higher order bit, lower order bit notation is to say let's assume for the sake of argument P is actually power of 2, so we can argue about this cleanly without having to consider any ugliness. So we have our matrix, A concatenated with C, and then we write our A as we decompose it into higher order and lower order bits, and then all we're going to do is we're going to search for collisions in the higher order bits, but we're going to do arithmetic on the whole thing. Right? That's really all we're doing. And so to map this back to the notation we had earlier, so the higher order bits, that's the scaled one, right, after modular switching, and the lower order bits is the thing that we rounded off, the noise that is produced. You do arithmetic in high precision, you check for collisions in low precision. Right? And so this way you only manage these tables for the most significant kappa bits, and so your tables get smaller. And so what we are doing when in the language of linear algebra, when we're doing BKW without lazy modular switching, then what you're looking for is essentially a small and sparse matrix that you multiply from the left with your A and C in order to produce something that is 0 here. You eliminate all those columns, and then you check if something is small here. And then what you're doing, if you're doing the lazy modular switching, you're still looking for a small and sparse matrix, but the demand against this matrix now is only that it actually produces something small over here. You don't actually need to reduce all the way down to 0, and then you check if this is still small. And why is this kind of beneficial compared to the one-off modular switching, just applying it and run your BKW, is if you do it at the beginning, then essentially you're introducing this rounding noise and then you're doing your BKW. So that can then, when you do arithmetic, that can then escalate. But for example, for the last few columns, I don't actually need to introduce any rounding noise at the point of when I'm working on the first few columns. So I'm just delaying actually introducing that rounding noise, and then those last few columns, that noise will not kind of grow much because I'm not doing very many operations on those once I've introduced noise there. Right, so what this buys me is I can reduce P by an additional factor of square root A over 2.
What's A again?
A is the number of tables I have. Okay? And then in a way the transition to Thomas' talk is to turn actually the thing that I've just sold you as a great feature of this algorithm around as a problem. Right, I said like this algorithm is great because I only have this huge noise contribution from the first few columns, but I don't have that much noise contribution from the last few columns. This is why it's better than straightforward modular switching, because there I have noise contributions across the table. But then you can also say like, well, that's a bit unfortunate, right? So because then I have this noise contribution from the first few columns, I really would like to reduce that. And that's, I guess, the motivation for improving this algorithm further. And as you will see, you can get some quite impressive results. So maybe the easiest way of showing this is again in the form of a picture. So we have this matrix AC, and then we create this table, right? So this is the table, the first table that is supposed to eliminate the first block of B columns. And light blue is something that is small in this picture, right? So all I've done so far is I've scanned my table and I've extracted the right columns to make my table. So in the next step I can now eliminate, right? Which I've now done. Now I go back through my matrix, and I use my elimination table T0 to actually make all the entries in the first block small. Now, next step, I move on to the second table. I do the same thing. I scan through my table. I find all the possible values. I put that in a table called T1. And then now I'm ready to say like, now let's use T1 to actually eliminate the entries in the second block. So what now happened is I accomplished my mission in the second block because I just made this small per design, but I just added two small things together in the first block. Right? So this noise now grows back. And that is really annoying because this will continue happening. But it will continue to happen to a lesser extent here, because this is already a little bit bigger than that one, actually roughly a factor of 2 or square root factor of 2, depending on what you mean by big. Right, and this will actually continue. So what I have is the noise actually from the first block. That is really the noise that is killing me. And then everything else will be smaller and smaller. So really the annoying bit, so I saw it as a feature of the algorithm, right? So back here I don't get much noise. But I can turn this around and say like, yeah, but back here I do get a lot of noise. So I want to avoid that. So the only way we figured out how to deal with that is something that we thought would be funny to call unnatural selection. And that is just to say, what I have in these guys, when I look at these, actually I have a lot more samples to play with than with later ones, because I'm using up samples to actually do my reductions and so on. So what I can do is I can work a bit harder on these first few tables, just to, maybe by chance, I just find something that's exceptionally short. Right, so I have this thing like, oh, it needs to be at least this short in order to fit in my table. But let's maybe produce something that is exceptionally short by chance. And you have a better chance of finding something that's exceptionally short in the first column because more samples pass by that you can test. Right, that was our approach in this PKC paper. The second approach.
What do you mean? I mean, the distribution is uniform, so it won't deviate too much, right, from the expectation.
No, but so what I have is I do my So
what is unnaturally short? So
yeah, so when I look for this table, in this picture they're both the same shade of light blue. But I have many rows here. So what I can do is I can try to find a bunch of rows where this is exceptionally light. Right, and because it's uniform, or actually these are small, they're not uniform anymore, I can just, like by chance, I might hit something that actually happens to be, like maybe I hit something that has 2 zeros here.
Can you quantify this?
Well, we give an attempt of quantifying it, but it's really muddy. Like it's not really nice. So it's based on some observations, and then you make some crazy conjectures, and then you have something that seems to somehow match what you do in your experiments. But I think that's one of the issues of like how do you actually make this work precisely, because the problem is not only asking how often do you find something in the first table, that's easy enough, but then okay, now I have a different distribution because I'm doing essentially rejection sampling on these guys, and now I'm adding them up. What is the distribution of the sums?
Yeah. Except for about Q, which tells everything that you convert what to flow.
So. And then the second approach.
Like if you want to sort of filter by putting 0 in the first couple of columns.
What happens if you take zeros in the first couple of columns? You restrict to 0 and then you start your error later, right?
Yeah. So that's a strategy that is used. It's actually one of the strategies in the coded BKW, where the first few columns you do normal BKW.
I was more thinking about pre-selection, that you just sample, that you just restrict your samples from the onset to have 0, even without any adding.
Yeah. So
that's also.
Yeah, you can. Yeah, you can have that as a pre-processing step as well, at the cost of however many samples. Yeah. Yep. And then the other strategy that you can do is, so what we did is all these tables have the same width, but the first table really really contributes to most of the noise. So what you want is you want actually to say like, I want to produce smaller elements in there, I want to keep the noise, make the noise smaller, but then your complexity explodes. So what you do is you make the first table narrow, and you make your tables wider as you go along. And that's the approach by Paul Kirchner, Pierre-Alain Fouque. It was published at Crypto this year, where you essentially increase the block size as you go along. And then this approach is generalized, if you like. In parallel was generalized. I don't know if that's a thing you can say. But there's this very nice algorithm coded BKW, where you use the power of coding theory to make that happen. So that's a more general version, as far as I understand, of the same idea, and Thomas can tell you everything about it. Right, that's all I have to say for now, and I'm not doing any kind of bragging slides with kind of how long does it take, because I hope Thomas will tell you kind of what do current state-of-the-art BKW servers actually achieve. But if you want to kind of work out, right, I advertise like, oh, we need to pick parameters for LWE instances, how do we do that? So what we have worked on recently is something we call an LWE estimator. It's a Sage script where you plug in your N, alpha, and Q, and then it tells you how long all the algorithms that we know of run. So it's a good way of saying like, okay, at least against the standard algorithms that we know of, if you want to kind of check how good are my parameters, then that might be an address you want to keep in mind. Thank you. Questions?
Just one question, because actually I used that like 2 days ago for just some recent work. Does it already include the most recent versions of BKW?
There is a branch called New BKW, and the coded BKW is in there, but I have not managed yet to actually reproduce the tables by Paul Kirchner. So the coded ones, like it's in there in a separate branch, but there is code there for the Kirchner-Fouque algorithm as well, but it just won't give you the impressive results that they report in the paper. But I haven't had time to actually look into that in more detail.
Can you go back to the slide with the symptotic complexity? Was this B to the B. Here. So assume that the B and actually the overall complexity depends not only on the standard deviation of S, but rather on the fraction.
Yeah.
CS over the original noise.
Yeah.
So what that means is that my original noise is 0, 0, 1.
Yeah.
Well, binary.
Yeah.
And my S is also binary. That means it's essentially 1 and it means that it won't have, well, it won't happen this time.
So what this really exploits is that the secret is smaller.
Smaller than the noise.
Yes.
I see.
So we were also very disappointed when we found that out.
How do you actually make this estimate of LWE? Because I think that's a very interesting contribution. So it's purely based on the formulas in the papers, right?
Yes.
It's not like you would do it for factoring where you have like experiments and then for the rest, so you have experiments up to 768 and then for the rest to 1024 you extrapolate the formulas.
It depends a bit because there's so many different algorithms. So for lattice reduction, that's pretty much what you have to do. So you kind of either run your favorite open source lattice reduction software and then extrapolate from that and get really bad running times. Or you take the complexities that are reported in the literature and use those to extrapolate. But then you use that.
Extrapolation is not clear which formula you take, for instance, for lattices, right? That's much harder.
Funny you mention that. Indeed, yeah. So we wrote a survey where we also explain kind of how we do that, and then you're right. Then people yell at you that you used the wrong kind of extrapolation. And
but nobody did the right thing, so that's
it's really, but I think the difficult part is that it's hard for us to estimate how long lattice reduction actually takes. It's a bit of like when you don't have big O's everywhere, when you try to really get it down. So at least for me, and so we explain what choice we made. But it is very clearly a choice, and so it's plausible that kind of this will need to be revised in the future.
One more question which I have for every speaker, it's a white paper question. So what would be the greatest challenge for you here in this area, BKW, LWE? Is it the parameter generation? Or?
I think certainly kind of, so having a good open source implementation that implements all the tricks of BKZ, like lattice reduction, I think that's a big contribution that nobody wants to make because it's a lot of work and you don't really get any credit for it. So it's a bit, that's an annoying thing that needs to be worked on. And then I think we can push BKW a bit further. So I guess that would be also interesting.
You were speaking about BKW only, right? Not BKZ.
No, so like the big challenge I would say is actually to have a better understanding of how long does BKZ actually run. And then, but kind of trying to bind it back, like there certainly is a bit of room for improvement here. And then my personal goal is, so it's actually going back to this question, is when it really exploits that the secret is exceptionally small compared to the noise. And the FHE parameters, they have such a small secret. So the Hamming weight is 64 no matter how big the dimension. None of these tricks work. So you look surprised. So in the implementation of the first implementation of AES for FHE, the way they
N2 base FHE or LWE ones?
The HE-lib, which is BGV, is that right?
Yes, it's based on LWE, ring LWE.
And then however big you pick your dimension, the Hamming weight is 64. It's a really small secret. But so when you look at actually all the algorithms seem to be running the same amount of time. So like I think actually trying to either, this is just really good and you can't do anything, or maybe there's something there. I would say that would be an interesting target to actually look at these parameter sets and see if you can actually lower the complexity of solving those.
So if it's fixed weight, why don't you take RORG then? then you get kind of noise-free.
Yeah, asymptotically that's very efficient, but the constants in a ROAG, they are ridiculous. And trust me, I would be the first person who would love to actually have an algebraic algorithm that is really good for these problems. But
ROAG. So where you
yes. So we tried, and
you tried already.
yeah. So the asymptotics are nice, but the constants, they're huge.
I kind of agree with you with this BKZ thing, right? So, I mean, we have this NTL, it's now a standard for every lattice reduction, but it's not the right algorithm that is implemented there. So it's a very old version of BKC. And, but I don't agree that you don't get credit if you do a proper implementation. I mean, Schupp got a lot of credit for his library. I think he's no longer willing to maintain it or update it or something. But
let me correct a few things. Victor Schupp is working on NTL again, and NTL is kind of receiving a lot of attention, and it's actually, it looks really nice. We just kind of posted a bunch of benchmarks comparing Flint and NTL on the Sage development mailing list. So Victor's working on that again. I don't think he's working on lattice reduction though. There is FPLL, which implements some of the tricks of BKZ 2.0. But it doesn't do extreme pruning, and that's the main thing of trying to figure out how do we pick our extreme pruning parameters and then make all that work nicely. And then, like, yes, I think we really want that, right? So somebody who would do that would actually receive at least the gratitude of a lot of people. If that means much in front of a hiring committee is a different question, but yeah, it's certainly something that is badly needed.
People have done it, but they are not willing to share, right?
There's actually a patch. I don't know. Have you tried it? So there's this patch for NTL that does BKZ 2.0, but
it was a patch. No, I didn't find the time to try.
So yeah. So there's some stuff out there, and some steps are being taken.
So, one of my take, if this is to be done, is that we would want a very long algorithm like the enumeration or the sieve to be run in C or C++, but then on top of this we want higher language, because the way all those algorithms are combined and optimized and finely tuned, this we don't want to do in low language. So my dream library for this is like high level Python and C on the bottom for the very fast algorithm. But this is like a big project.
Yeah, that makes sense. Yeah.
That's easy to do that.
Huh?
That seems, because you can just call the SVP and FPLL already in Sage, so we can make that work.
Yes, but when you want to give the parameter, if you want to give pruning, I mean, you want them to be a bit, you want to have more tuning options.
True.
So sorry for the long discussion. In Sage, you can already call your favorite SVP solver inside BKZ, or?
No, but the SVP solver from FPLL, so it's an enumeration. You can call that from Sage, and you can even pass it your own pruning parameters if you want. So that high-level interface is at least in my branch of Sage, which I'm sure I've pushed to track somewhere. But yeah, it can be done.